Yeah, so then again, good morning, afternoon, and welcome to this presentation on radio design from the perspective of Hexa-X-II Work Package 4. My name is Ahmad Nimr from TU Dresden, co-leading this Work Package 4 with Nurul Mahmoud from University of Oulu. So here is the outline of this presentation, and meanwhile, I would like to thank all the WorkPackage 4 partners from different areas of academia industry. So let's warm up first with some more general view before deep diving into the activities in the WorkPackage 4. Yeah, so let's talk about the radio design concept, and this is in general is applied in many domains of life, like designing a house or even designing like workshop like this. So we have the inputs and we have the outputs, and yeah, so each design scope has different terminologies. So for radio design, the terminologies are, so we have the use cases as input, and these are described by various attributes: environment, user devices, connection density, mobility conditions, and most importantly, the service requirements. And there are inputs related to constraints for regulatory, like frequency in terms of the frequency band and or range and bandwidth, the power level, and others. And then we have other considerations like value considerations for trustworthiness, including security, privacy, reliability, sustainability, not only in terms of energy efficiency, but also material cost and other aspects of social and environmental sustainability that are discussed yesterday in Work Package 1 presentation from Hexa-X. Inclusiveness also covers a lot of aspects. One of them could be like when talking about designing affordable cost for devices. Of course, scalability and flexibility are important in the design, because the design should not focus on a specific scenario, and at the same time it should not target to get only the extreme cases. So there should be a level of flexibility. And the design is about using resources, and these resources are hardware resources and software component, and of course energy sources. And now how these resources are also limited, and they are constrained also by the other constraints and regularity and also the sustainability, for instance. And then the radio design needs to use these limited resources to fulfill the requirement and respect the constraints. And the outcomes is going to be the design description. This is what are the selected technologies, architecture, signal flows, and the interaction between components. And after getting the design draft, we do the validation, simulation, prototyping. Okay, so we have a lot of things like trying to constrain our radio design, and then we need something to help us. So there comes the enablers. So the enablers are any technologies or tools that helps in the design for achieving its goals and to try to overcome the challenges and the constraints. For instance, we have to overcome the frequency limitation. We need to open new spectrums. We need some mechanism for sharing. So new spectrums, for example, sub-terahertz. We need technologies to improve the hardware usage, like joint communication and sensing, to provide multiple functionalities. We need new simulation and modeling tools to model the hardware, to understand the environment. So we are not going to do measurement all the time. So we need this kind of modeling, and it comes here, the channel modeling activities. We need also new computational tools such as AI, and then some technologies to overcome the impact of the environment, like REST technologies, and also solutions for fulfilling the constraints of the values related to trustworthiness, sustainability, and so on. And here it comes then the enablers. It's a very long list of enablers, and in Hexa-X-II Work Package 4, we focus on these highlighted ones in blue, and there leads me to the structure of WorkPackage 4. So we have 5 tasks. One of them is focused on the terahertz communication, and here we restudy all the technologies related to opening new spectrums, like waveforms and modulation, MIMO techniques, and also the channel modeling. The other tasks focus on improving the existing system in FR1 and FR2, and they're mostly focusing on the AI/ML solutions, in addition to the integration of the DMIMO REST technologies. Joint communication and sensing also is considered for different frequencies, different sensing deployment or architectures, work on waveforms and resource allocation. We have a task focused solely on flexible spectrum access, sharing, coexistence, low latency access, multi-rate, and also about interference, mitigation. And all these 4 tasks now focus on a specific technology. We integrate them in the holistic radio design task, focusing on the flexibility and also enhancing the value parameters. Yeah, how to proceed now, how to understand the requirement. There are so many use cases. What are the requirements? So here is the target. So the initial stage is to define radio scenarios, and these radio scenarios are defined based on some extreme requirements. So we took use cases from Hexa-X, some exemplary use cases. They were well studied and characterized by many industrial partners, so giving service requirement in terms of communication, localization, and sensing. These are service requirement. We take the service requirement, map them to radio requirement. For instance, availability could be mapped. Availability and reliability in the service is mapped to the coverage, reliability impacted by radio interface, reliability and latency, and so on and so forth. Sensing requirement mostly identical. Then we characterize them in a group of extreme requirements. That results in 4 scenarios. One focused on extreme coverage, other on extreme data rate, extreme connection density, and low latency, and high reliability with extreme requirements. And these 4 radio scenarios just described by the requirement. And then the radio design would be focused on a specific scenario, and of course, not forgetting about the value constraints. So here it's more numbers for the extreme requirements. So we have the radio scenarios, and similar activities was or have been at the same time carried out by ITU, and they also define user scenarios. And here then we try to map our scenarios to the ITU scenarios with some example use cases. So the extreme coverage map to ubiquitous connectivity, extreme data rate covers 2 use scenario in ITU, intelligence and communication, immersive communication. The extreme connection density also cover immersive communication and massive communication. Then the extreme low latency, that's called hyper in the TU, hyper reliable and low latency communication, also integrated communication and sensing. So the green field here highlight the extreme requirement, and this is aligned also with the requirement by IMT 2030. So for coverage, so the extreme case for the coverage require the availability up to 6 nines or 8 nines. Ultra high data rate up to 100 gigabit per second, then the extreme connection density up to 10 to the power 8 device per kilometer square. And of course, here we should also think about the 3D coverage, then the extreme cases for low latency. And the nice thing about that for each scenario, there are not only extreme requirement, but some of the requirements are very relaxed, and this is highlighted in blue, and the others are variable. For instance, when it comes to extreme low latency and high reliability, the data rate is really low. So that is good news. And these scenarios then can serve most of the use cases that encountered for 6G. And when talking now about radio scenario in the context of requirement, there are radio scenario parameters, and this is where we define also the other parameters related to scenarios. So let's call them here the sub-scenarios. Extreme coverage, we need to cover wider area, so you are not going to use only a single scenario for that, but there could be different sub-scenarios involving different environment, different frequencies, also with different mobility. So here, for instance, an example about extreme coverage that's covered by terrestrial and non-terrestrial network. And the frequency here, the frequency column just lists some of the options for the frequency band that can be used to fulfill this user scenario. Yeah, and here are like the four specific scenarios we are gonna evaluate and assess the performance during the work of WorkPackage 4 and Hexa-X-II. Okay, how to assess this work? We have the performance metrics, and the performance metrics are the conventional one for communication and sensing. And for each of the metrics, like the KPI for data rate, there could be different metrics depending on the area of study. Could be the big data rate for the hardware design guys, it could be the throughput, could be capacity, coverage, also different terms, and for R's, maybe outage probability. And the same applied for also the other metrics. So they are well known and there are different metrics for each KPI. Then we evaluate also general performance requirement like the energy efficiency, and there are a couple of definitions also in the projects. Might go beyond the energy per bit, so to have more sense of the actual output power to the input, to the total power consumption, complexity, not only the computational, but also the amount of hardware resources needed, the cost. So this might go beyond also our work. So to assess the cost could involve other partners there to help out. For the value requirement, also this about the KPIs. Some of the KPIs or the KPIs are the process of defining these KPIs in progress by WorkPackage 1 and Hexa-X, but you can have some feeling about it, like how to measure the inclusiveness, maybe what could be the percentage of coverage, what could be the price of devices. This could be estimated by the hardware designers. For reliability, we have already some measures. For security, there are some work ongoing for the physical layer security measure. The same goes for sustainability. At least we have one tool to evaluate the electromagnetic field exposure. I will talk about it later. Yeah, and after this long introduction, now we come to the more technical deep dive into the holistic radio design. So here is the framework, so including all the components. So let's look at the different component. We have the propagation, and this is related to the use cases. And then we have the radio front end that provide also the operating frequency and the antennas, and all of them, they form the wireless channel. And this could be subject then to the architecture and deployment. So this wireless channel is affected by these architecture and deployment options. After that comes the RF circuit interfacing with the antennas, and here we need to do the modeling for the hardware. And here it comes the baseband. Then the DAC ADC are also important topics for the radio design, especially when talking about wide bandwidth. ADC becomes important for the energy efficiency. And it comes the abstraction of the hardware and channel, and this is what is important for the people who are working on the physical layer aspects, which mostly software, but of course also the hardware implementation of the signal processing is related. And the PHY then offer the transport channels to the MAC, and at this point here, what we call radio link. So the input from the MAC layer of the transmitter and the output to the MAC layer from the receiver. This is the end-to-end radio link. And so our work here is cover different areas. So the protocols and the upper layers are studied in WorkPackage 2 and Hexa-X. But here we focus more on enablers related to the radio itself. And the goal again is to integrate different components and have end-to-end design optimization. Here next, I will give some ideas about the items studied in Hexa in this work package. So we group them into different categories of enablers, architecture and deployment, several topics related to distributed MIMO and address transmission, so addressing the backhaul, integrated access and backhaul, risk-assisted communication, and different schemes for T-MIMO, even considering 1-bit ADC, different massive MIMO architecture from hybrid, analog and digital, or even some items will focus on fully digital architecture with low resolution ADC. We have an item related to flexible transceiver architecture. Here, it's also maybe more related to the gearbox concept that introduced in the previous presentation, where we could do the reconfigurability of the hardware and also the transmission schemes according to the situation. That is the channel and the demands. We have also the joint communication and sensing architecture in different architecture, like monostatic, bistatic, multistatic, even the integration with or using non-network assisting the terrestrial sensing. Signal processing is a wide topic, covers so many aspects. This is not only model-based, but also AI-based. And regarding the waveforms, some of the optimization for the waveforms for different frequency bands, some activities to design the constellation for FR1, FR2, some other to investigate new waveforms like zero-crossing modulation for sub-terahertz waveform, also learning and learning of the constellation. So where not only the conventional QAM is used here, but might result in some learned patterns. Of course, signal processing for MIMO schemes and the MIMO, from channel estimation to coherent and coherent detection. And a lot of activities are trying to also explore AI there. Signal processing for communication and sensing covers also the waveform design or precoding for JCAS, optimizing the resource allocation for communication and sensing, and a lot of more. So the list is really long in this huge work package. And regarding flexible spectrum access, so these activities are more at the MAC side. As mentioned before, this task is focused on the studying different spectrum sharing mechanism and coexistence, evaluating or assisting the interference between terrestrial and non-terrestrial network for sharing these spectrums, studying low latency random access mechanisms, especially for sub-terahertz. We have items related to enhancement of the integration between terrestrial and non-terrestrial networks. And also one study item related to the broadcastive resource management, and this is also at more at the MAC layer. Here, other enablers more focused on the I or the value, sustainability, security, resilience. One part of them is about how to optimize the transmission parameters. Given that we have a flexible transceiver, it has capabilities. How can I configure these capabilities to get the best performance? And here it comes this activity about optimizing the parameters. So this optimization could be like some of it in real time, some other for a longer period. Physical layer security, also a small contribution in this project. It's covered one item about secret key generation. We have resilience schemes, for instance, jammer localization, and this, even though this scenario is for sensor network, but can be also applied to the distributed MIMO case, and several activities in the context of GCAS, like for security and privacy. As mentioned before, also modeling and simulation tools are important for the radio design. And here we have main activity, continuing actually the activities in X about channel modeling for sub-terahertz, doing measurement and then modeling. And there are other activities related to coverage analysis at different frequency bands. And we have recently started some activities on JCAS channel modeling. Other simulation tools, including the electromagnetic field exposure.
I think you are quite in the end part of the presentation, but we should also go.
Yes. And this mostly for massive or distributed MIMO environment. Of course, link level simulator. This is based on 3GPP, evaluating different type of channels, especially when talking about sub-terahertz. This is also important to assess the suitability of off-beam-based waveform, or if we need a new waveforms. Finally, we have the proof of concepts for prototyping to evaluate some of these enablers. For instance, about JCAS demonstrator, this is where we show the feasibility of using or sharing the hardware spectrum between communication and sensing functions. One proof of concept on showing the AI native air interface about learning the constellation, and this also to be demonstrated. Measurement, as I mentioned before, especially for sub-terahertz, and maybe it will also, let's see if there will be resources to start also some activities in the range 7 to 15 gigahertz. And finally, flexible transceiver, and this is SDR-based proof of concept to show the concept of flexibility and the gearbox idea. And for more details, deliverable 4.2 is available, and we have description of all these enablers in WorkPackage Core, and early results and evaluation are coming in May. So that's all from my side. Thank you.